Hey,
Hey, how are you?
good, how are you?
Good, thanks.
Nice to meet you, Stephanie. Is that right?
Yes, yeah, nice to meet you too. Can you let me know how I properly pronounce your name? I didn't want to like mispronounce it.
Yes, that's right. Jahnavi.
Jahnavi. Okay, gotcha. Cool.
Mm-hmm.
I just didn't want to like mispronounce your name when I introduced you to like the entire students
I
that are here
appreciate
today.
it. Thank you.
Yeah, no problem. And is your last name just Shaw?
Yes.
Okay, cool.
Am
Jah.
I coming out choppy at all? Because my house internet is a little finicky.
You're fine for me, so that's good.
Okay, perfect. Okay.
Perfect. Have you tried sharing your screen? Does it allow you to do that? I just wanted to make sure before we started.
It should, let's see.
Mhm. It should. I think I made you the co-host, so hopefully it works. Yay,
Just make sure it
perfect.
works in presenter mode.
Yeah, for sure.
Can
Awesome.
you
Yeah, and you don't have
see
to
the
share it like
notes or
right
just,
now, but it's up to you. Just wanted to
can
make
you
sure.
see the notes or can you just see the slides?
I can see the slides.
Okay, perfect.
Yeah. Awesome.
I just have a quick question about the recording.
Yeah, absolutely.
Where exactly is it going to be available to, and like who's going to have access to that?
Yeah, for sure. So we kind of have like this file that we're uploading, like all the moderators for all the sessions are like responsible for uploading the recordings. So any of the students that registered for this session will have access to that recording. And we can send it
Okay.
to you as well if you'd like.
Yes, please. Yeah, that'd be nice. Thanks.
Yeah, for sure. Yeah, so we'll just keep people a few more minutes here. I know there was a session right before this one, so give people a couple more
Yeah.
minutes.
Mm-hmm.
Yeah.
So if I understand correctly, are you also part of the program?
Yes, I am. Yeah, and I'm on ESC this year, the student council. So we're helping out with just moderating the sessions for this week.
Very cool.
And then for the question and answer period, you're good with just like having students like send questions in through the chat, and I can help moderate those for you.
Perfect.
Yeah. Okay, sounds good.
Yep. And because it's not a webinar feature, I hope it's
Mhm.
okay if I try to make it engaging and interactive.
Oh yeah.
I would like audience participation. So it'd be
Yeah,
nice.
no, definitely. Yeah, those ones definitely keep the students more engaged. So that's perfect. Yeah, no,
Okay.
definitely interact with the students if you'd like, for sure.
Okay.
Yeah, because we kind of tell them
Maybe.
just for, sorry, go ahead.
Oh, sorry, I was just gonna say it might be a little bit less than 40 minutes. Um,
No
but I'm
worries.
hoping there's like questions and discussions afterwards. So
Yeah, no, no worries at all. That sounds great. All right. Good morning, everyone. Just before we begin, I'll do a quick introduction here. So my name is Stephanie, and I'm the current French program rep on ESC this year, and I'll be your moderator for the session today called Remote Sensing in the Classroom. So we'd like to start off by thanking our speaker, Jahnavi Shah, for taking the time from her busy schedule to share her knowledge and expertise with us. So this session will include a 40-minute presentation followed by a 20-minute Q&A. So please turn your audio and video off for the duration of the presentation, and for the Q&A discussion, please use the chat box and I'll do my best to monitor the questions from there. And in case we don't have any questions, we will hand the session back over to the speaker to share any additional information regarding the topic being discussed. And finally, just as a reminder, make sure you guys fill out your Check for Understanding forms, which you can find on the Teacher Candidate Conference Week website. So yeah, that's it from me. And now I'm just going to turn it over to Jahnavi.
Thank you very much, Stephanie. I just have a quick question before you get started. Is it possible to allow people to have their video and audio on to chime in during the presentation?
Yeah, absolutely. We just ask them that so they don't, we don't hear anybody's audio on during the background or anything. But yeah, if you want to have an interactive piece, like everyone, feel free to come off mic or video as well, or video.
Yeah, so I was going to say, if you feel comfortable, you can leave your video on, and obviously if you have questions, you can chime in, turn your audio on. So I want to make it a little bit more interactive and engaging. So feel free to type it in the chat box, but also feel free to unmute yourself if you have questions. Feel free to stop me at any point, really. I'm hoping that, this can be a little more of a discussion.
Are you going to show the slides?
Yes, I will.
Okay.
So I'm just going to start the screen share. Can you see my slides okay? Okay, perfect. So we will get started. So like Stephanie said, today's session is going to be about remote sensing in the classroom. And I'm a PhD student in the Earth Science department, and my majors are Geophysics and Planetary Science. So to get started, a little bit about me. Like I said, I study planetary science, and I've always sort of been interested in space. And I think my journey is a little unconventional. So when I started off, I thought that if I wanted to study space, I had to do astronomy and physics, which is kind of true. It's helpful to have that, but there are so many other ways that you can get involved. So for my graduate studies, I decided to move into more earth sciences, which lets me study a little bit more about our solar system. And that's a little bit more tangible for me, I think. But so remote sensing is a big part of my work and what I do. So I have a little picture of Earth, and the little yellow circle that you see is Saturn's largest moon, Titan. I'll talk a little bit more about what I do and how I use remote sensing a little bit later in the presentation, but I just wanted to draw attention that these are special planetary bodies, and it's very important that we have remote sensing to study objects that are very far away from us. But it doesn't even have to be that far away. It's very applicable to what we do in our everyday lives, and it's very important to study our very own planet, Earth. So before we get started, I just want to kind of get an idea of what the audience thinks when I say remote sensing. What's the first thing that comes to your mind? If anyone's feeling brave to sort of take a guess, leave it in the chat box.
Can you see the chat box, Jahnavi?
Yes, I can. Perfect.
Okay, perfect. Yeah, I've got some stuff coming in.
Terraforming Mars, yes. Driving robots on the moon, satellite images, collecting data through rovers, GPS. These are all great answers, and to an extent, it includes all of them. So the technical definition of remote sensing is the acquisition of information of some property of an object or a phenomenon by a recording device that is not physical or in intimate contact with the object or the phenomena under study. So what you've said, so GPS, satellite images, they all are a part of this. And what's interesting is that us humans can also be remote sensors in a way. So if we were to think about our 5 senses, can you tell me, can someone take a guess as to what senses might be considered part of remote sensing based on the definitions? So remote sensing is essentially, you can't be in direct contact with it. So yes, sight is one of them. Smell and sound, exactly. So I know, when we talk about remote sensing, we get very technical and think about satellite images. But yeah, all 3 of our senses, excluding touch and taste, we're not in direct contact with that object. So technically, part of us is a remote sensor in a way. So there are, I think, 7 main important points when we talk about remote sensing. There are some that I'm going to skip over because they're a little bit technical, but I kind of want to hit the main points. So the first and foremost is the energy source or illumination. So the first thing that's important when we're trying to look at an object is that we need it to be lit up. Otherwise, we can't see it. And there are different ways of doing this. You can have something else lighting it up. You can have the sensor itself light up the object that you're trying to study. But so yeah, energy source is the first. The second is radiation and atmosphere. So usually when we're studying through remote sensing techniques, like I said, it's remote. So you have interference with, for example, the atmosphere when we're studying the Earth. So it's important to understand how your energy source might interact with what's in the atmosphere. The third part is how it interacts with the target itself. So light, so most of the times you use light when you're using remote sensing. So it's important to understand how it's going to interact with the target that you're trying to study. And we'll get into this a little bit more in the next slide. The fourth thing is the recording of energy by the sensor. So once your energy source has interacted with the target, we need to make sure that the response from it gets recorded in the sensor. The fifth part is the processing of this recorded data. And then 6 is interpretation and analysis. And this is something that we'll actually do a little bit later in the session, where you'll get to participate in trying to understand what we're looking at. And the last part is about applications. So now that you've looked at an object, collected the data, you've interpreted it, what does that mean? What does that tell you about the object and anything related to it? Why is it important that we study that? Okay, so as I mentioned, the first part is how it interacts, the energy source. So usually how it's done is you have a light source, but it's not limited to it. Like we talked about how sound is also considered remote sensing. So it doesn't necessarily have to be the electromagnetic spectrum. But if you've taken high school physics class or any science class, I feel like this is one of the things that you talk about. So you have the EM spectrum here, and the way it works is that the EM spectrum helps remote sensors kind of decide what wavelength to use. So if you remember, we talked about how it's important to understand how it interacts with the atmosphere and also with the target itself. So different wavelengths help us study different objects of different sizes. And so for example, here in the top, I don't know if you can see my cursor. I'm hoping you can see it. But so in the top bar here, you have penetrates Earth's atmosphere. So this will become very important. This is very important when we do study Earth and other planetary bodies that have atmospheres. So if we're trying to study Earth based on this diagram here, if we're trying to study the surface of Earth, which wavelengths would work? Because not all would. So here, Y and stand for yes and no. So it's here if someone could kind of point out which wavelengths would be best when studying Earth. Feel free to chime in. Oh, perfect. Radio and visible, that's right. So hint, I work with radio waves, which we'll talk about a little bit later. And it's one of my favorite ones, completely unbiased. So there's a comment saying that you use energy with long wavelengths. That's not necessarily true. It's just a different frequency. So it has lower energy, but it's useful for studying objects that might be a little bit bigger. So if you have particular, so for example, with radio waves, if there are like these smaller particles in the atmosphere. So if you're using a very small wavelength, it can't travel through the molecules in the atmosphere, and it won't let us penetrate it to be able to look at the surface. So in that case, a longer wavelength is actually useful because it won't really interact with it, and it'll penetrate through. So one of the neat things that I really like about remote sensing is, as humans, we're limited to this visible range. And as we can see that there are other wavelengths that we can use. So for example, planetary scientists will look at the characteristics of a planet and based on that decide what part of the EM spectrum is best to study the object or the feature of interest. And what's really cool is that because we're remote sensing, we have access to all of this, whereas we wouldn't have that if we were studying it in person. So for example, field studies, when we go to, so for like geologists will go to the field to collect samples, and this is true for any sort of scientist that would need to do field work. If you go, you collect samples, you're still very limited to what you can see, but these instruments and remote sensing helps us collect data at different wavelengths. And in a way, it's also, so equipment might be very expensive, but on a larger context, it is much cheaper than being able to, go to certain field sites that are too expensive or sometimes a little inaccessible to travel to. So this is a way of using remote sensing to study something that we wouldn't be able to study otherwise. For example, the outer solar system. We haven't been able to send any rovers or humans that far, but we have sent satellites that can go that far and collect data for us, and then we can make interpretations based on that. Okay, so now we're going to get into a little bit of the different types of remote sensing. And this is just a quick thing to give you an idea of the different, how there's two main types. So there's passive remote sensing and there's active remote sensing. So this has to do with the energy source that we talked about at the very beginning, which is sort of the first points when we're looking at remote sensing. So on the left, we have a depiction of passive. So looking at these two figures here, can someone take a guess as to what the difference might be here? So what do you notice that's different?
Yeah, go ahead, Flo. Sorry, I thought I saw someone raise their hand.
Oh, yep, I see someone. They can unmute if you would like.
Yeah, go for it, Flo.
Oh, sorry. Passive light is from a reflected source.
That's right. Yeah, and I think there's comments about it too. So that's perfect. Yes. So for a passive remote sensor, your energy source is not in your sensor. It's coming from elsewhere. And a very common one is our sun. And so the active one, then by default, is when you have your energy source on the sensor. So now kind of having understood the difference between the two modes of remote sensing, can you think of examples of these two different ways of remote sensing? What is one instrument that you might use that is a passive remote sensor? And these can be things that you actually use in your day-to-day lives. A lamp, exactly. So, if you want to navigate through your room, a lamp is a passive remote sensor. Well, so the lamp would be the energy source. What would be the instrument that you're using that would make it a passive remote sensor. Yeah, exactly, your eyes. And then what might be an example of an active remote sensor? Camera with a flash on, that's exactly right. So your, yeah, exactly. Night vision goggles, all of them have an inbuilt source of illumination. So that's exactly right. Your phone can also act as a remote sensor. So it's very similar to the camera with the flash on. So let's say if I'm taking a picture with my phone, just using the lighting in my room, that's passive remote sensing. But if I were to turn the flash on, then I've turned it into an active device. So when we first talked about remote sensing, we people said that, you know, satellites is one of the things that you think of when you say remote sensing, and that's absolutely correct. So we have different satellites and sensors, and there's three main ones that we use. So there's ground-based sensors. So for example, on the right here, we have an image of a ground-based telescope. So that's one way to do remote sensing. The other one is to have air remote sensors. So, you know, there's lots of planes, there's drones. So aerial photography is one of the common examples of air remote sensing. And the other one is obviously in space. So orbital satellites that either are orbiting planets or planetary bodies or are flying by. So those are the three different ones that I can think of. But then we also have, like we mentioned, there are other devices that we use in day-to-day lives. There's also a very cool, it's not that new, but it is becoming more common way to study our atmosphere is through balloons. So, you know, you deploy a high altitude balloon and you can study the atmosphere in that way. And Western actually had a team who sent a balloon to space to study the different aerosols in the atmosphere, which I think is pretty cool that we can do that. And so sensors and satellites are important for the point when we talked about that recording of the energy part of remote sensing. So you've illuminated it, you've looked at it, and now it's time to record it with your sensor. So I think one of the most important parts about when we're talking about remote sensing is its applications. So there are very technical parts to the concept of remote sensing, which I'm not going to get into today. I think it's important to focus on the applications and why it matters to us and why we use it and how it helps our day-to-day lives. So I've mentioned that I use it to study planetary science, but there are some very more, I think, personal and relatable applications to it for Earth itself. So this is one of the first ones, and I do this because this was the first sort of civilian application of remote sensing satellites. Civilian in the sense, like, as opposed to military uses. So I think remote sensing it came into development for military uses. So based on this image, what do you think the first application, non-military application of remote sensing was? Weather, exactly. So everyone got it, perfect. Yeah, so this is a satellite that was launched by the United States in 1960. And it's basically, yeah, so it's meant to monitor weather. So it can track clouds, rainfall, forest fires even, atmospheric moisture, how the clouds are moving, which are very important to studying the different weather patterns here on Earth. And to that extent, can be applied to any other planetary body with an active atmosphere. Okay, so now we're going to get into some fun little examples of images. So it'd be really nice to have some participation just based on the images. So one of the main applications why we use remote sensing for Earth is for land observation. So here in this image, the green represents forests. That's a hint. So what might we be looking at in this picture? Take your wildest guess. And that's perfect. So Ryan says, and Jill, they both say deforestation, which is definitely correct. So here you have a map of forest clear cutting. So it shows how the green space has been reduced, has been cut over these few years. So one of the direct applications is for forestry. So there are a lot of mapping studies done. So we use temporal studies. So we'll look at a specific site and collect satellite data over, different time periods and try to study the different patterns of deforestation. But this extends to also its effects. So we'll look at, infrastructure mapping and how that has contributed to the deforestation in that particular region. And the species and habitat changes as a result of that. So this is all something that we can study through land observation satellites. And in this, again, we're still looking at land observation. So can someone think of what these circles in this image might represent? Yes, so someone says Justin says lots of property. So there are some of them do represent like buildings and such, but I'm thinking more in terms of the green circles. Irrigated fields, yeah, so these are crop circles. So what's really cool about it is that we can track agriculture patterns. And here I have there's this really neat example. So based on what we said about irrigated fields, this is an example. This is a picture of crop fields. And we'll get into the interesting part about this. But what's important is that not only can we use it to look at agriculture patterns, mapping patterns, we can also look at, through remote sensing, we can try to identify what crops there are, what the condition of the crops is even, so we can tell if the plants are healthy or not. We can map different soil characteristics, so to figure out where the best place is to farm can be done through remote sensing. And we can also check how compliant the farming is to standard practices. So here, it goes a little bit more into sort of like the heritage aspect of it. So not only can we learn about, soil quality and what kind of crops are being farmed, but it also, gives you little bits of little history. So here on the left, we have Quebec fields, and on the right, we have Saskatchewan fields. And what do you notice in terms of the difference or the similarities between them? Try to look at its shape. How do you think they're different in terms of their shapes? Yep, so Flo says Quebec uses a French style division. That's right. So as you can see, the Quebec fields are more longer and narrower, whereas the Saskatchewan ones are a little bit more box style. And like Flo said, so the Quebec's farm field shapes are influenced by the French settlers, which is also true for some parts of Nova Scotia and New Brunswick, whereas the prairies are their square shape is more based on township standards. Yep, I see all the comments rolling in, and you're all right. Yep. So they're long. The Quebec ones are longer, whereas Saskatchewan is a more gridded system. So I just found this to be a little cool that, we can have applications, we can learn things from remote sensing data that is not just, related to science, but it gives you a little bit of history too. Okay, the other applications of this are for hydrology. So it has very real life and immediate applications and usefulness. Excuse me. So here we have a radar map that's mapping the floods of 1997 in the Manitoba Sea. So here, the dark material that you see here is the floodwater, and it's showing how it's surrounded this town that's depicted by B. So it helps us map extents of floods, and I don't want to get into too much of the technicalities, but to give you a little bit more insight as to how we're able to tell this is, so the town that's depicted by B is bright. So here we're looking at a radar image. So if you think back to the EM spectrum, these are the radio waves. So how they work is sort of, you're looking at the surface roughness. So for the town, you have more buildings and stuff. So you have a little bit more rough surface compared to the floodwater, which tends to, like, the top of the water layer would be very smooth, which is why you're getting a dark return. So that's how you're able to map sort of like the flood here using a radar image. And the other part, so we were looking at land observation satellites, but this can also be extended to marine observation. So this is very important when we're looking at ocean patterns, currents, sort of like, where they're like storm forecasting. We can also look at marine mammal assessment and fish stocks, which is not used by just the scientific industry, but also the fishing industry. So remote sensing has a wide range of applications and disciplines that use it for their, either for their studies, for work. And so one really neat thing is that when you're looking at, let's say, for example, fish stocks, what you're really looking at is sort of like, the water quality, the phytoplankton concentration. So here you have an image basically of different concentrations of phytoplanktons, which I think is really cool. So, there are many layers of being able to deduce what you're looking at and why that might be important to what you're studying. And in terms of climate change and applications such as environmental applications, we can also map oil spills and the extent of that to be able to help, deploy help and aid where it's needed. And as I mentioned earlier on, these applications are very important to Earth, but they extend much beyond. So for example, one thing that's really close to my heart is planetary science and space. So a more sort of grounded application for that is geology, which is essentially the study of landforms and structures and the subsurface and understanding the physical processes that are affecting a planet's surface, for example. And this is especially important for studying things like, potential hazards related to volcanoes, earthquakes, and landslides. So this is what we really use remote sensing for when we're speaking of studying geology. We can also use it to understand the composition and structure of not only our planet, but other planets such as Mars, shown here. And so what I wanted to talk about, and this is going to be a little interactive, so I wanted to talk a little bit about what I study and how I use remote sensing in my day-to-day research. So I study impact craters, which are essentially these circular like depressions that are created by rocks hitting the surface of planetary bodies. And as I mentioned before, I particularly study Saturn's moon Titan. So what's really interesting about this is it's very similar to Earth. So it's much smaller, but they have similarities, including that there's liquid on both surfaces. So Titan has lakes of liquid methane and ethane. And it also has a very thick atmosphere. So if you look at the image in the lower right corner, that's the haze that you see on Titan, which kind of looks similar to like, you know, a cloudy or a foggy day here on Earth. So if you can try to relate to that. So it has a very extended atmosphere. So if you think back to our electromagnetic spectrum, we said that there are certain wavelengths that are useful when we're looking at planets, for example, that have these thick atmospheres. So what's really useful is the use of radio waves, which is what I use to study Earth and Titan, because they have this thick atmosphere. And the only way we can actually look at the surface is if we have our source being able to penetrate through that thick atmosphere. So what I'm trying to look at is sort of identify these craters that I mentioned on the surface of Earth, which is really an analog for studying Titan. So like I mentioned, that these remote sensing devices are useful for studying something that's far away, but even then our reach is so limited that we need to, you know, pair up on similar studies. So the remote sensing data that we have available for Titan is extensive, but still in the grand context, it's still very little, which is why I study Earth as sort of like, you know, a comparative study. So this part is going to be hopefully very interactive. So feel free to chime in, and I'm going to give everyone a little bit of time to look at the images. So this is sort of to give you an idea of, you know, what might a planetary scientist slash a remote sensing scientist might do on a day-to-day basis. So we talked about, you know, looking at a source, collecting data, but then there's time to interpret the images and do some data analysis. So there are some pre-processing steps involved here, which we're not going to get into today. But let's say you're at work, you're a remote scientist for the day, remote sensing scientist for the day, and you've processed a bunch of radar data for these craters here on Earth. And so now you're presented with these images, and now it's time to sort of understand what you're seeing in the data. So what we're going to do is we're going to look for craters. So going back quickly to this figure here, craters tend to be circular in shape, and they tend to have a depression. So what we're going to do in the next couple images is try to look for these circular features. These examples are a little bit more simpler. So if everyone could take a couple seconds and try to find these circular features in both images. There might be more than one in each figure. So, you know, take some time and scan through the images to see if you can find these craters. And if you have a guess as to where these figures are, you can chime in, but I'll show you where they are located in a little bit. So as people are going through these images, if you want to leave sort of the number of craters that you see in the figures, that would be really interesting to see. You could just give me the total number of craters that you see in both figures. Feel free to unmute and shout it out. You can also leave it in the chat. how many craters do you see in these figures? Alexandra says that there's 10 in the first picture. Interesting. Okay. Justin says there's a big indent in the center in the left image, and in the right, there's a black spot about 2 to 3 kilometers, which looks fresh. Carolyn sees 3 in the right and left and 1 in the left. Oh, this is a very interesting range. Okay, so people are saying somewhere between 1 to 10. Okay, so we have a nice range of numbers, and it is very difficult, excuse me, it is very difficult to sort of identify this. And obviously I don't expect anyone to get it right off the bat. I've spent almost 2 years looking at images like this, and it still takes me a while to actually figure it out. And even then, I'm wrong half the time because it's so hard to interpret data. And it also gives you insight into sort of, you know, once you have all this remote sensing data, it's not as easy to draw analysis and interpretations from it. It takes a lot more work. So thank you for your guesses and trying to look for these craters. If I can go to the next slide, you can see where these craters are located. And to people who said that, you know, you might have seen more, that's totally understandable because there are other features in here that look circular, which may not be craters. So maybe we'll go on to a different example. So just quickly going back to make a point. So as we saw, there were guesses for more craters, and that's because we see other circular features, and it's hard to sort of, you know, strongly say that, you know, this is the crater and that these other features are not. So one really interesting part about remote sensing is that we can layer data. So, you know, if you're in the field, you only have access to the equipment that you have with you. But for example, if you're using remote sensing, you can have data from different wavelengths, things that looks into different features or different characteristics of that one feature. And then you can layer it on top and try to make better estimates about what you're looking at. So here we have another image, which is much, much more difficult than the previous ones. So the challenge here is to, again, take a couple of minutes and try to find the crater or craters in this image. Again, you're looking at a radar image. So once you've had a chance to look at it, leave your guesses in the chat box or feel free to unmute. Anyone have guesses for how many craters that they see? Zero. Flo says 0, and that was my first guess when I first looked at it as well. And maybe one just above the river. Okay. Justin, I'm guessing you're looking at this perhaps, hopefully. Perfect. Marianne says 2, okay. Okay, so so initially when I looked at it, I thought there was 0 as well. So what I was saying about layering data is, for example, we can add another set of data here. So here we're looking at radar data, but now we've added topography data. So here your reds and your yellows are high elevation areas, whereas the blues and the purples are lower elevation areas. So if you think back to the definition of a crater, it tends to be a depression. So now here's a chance to sort of reassess the image and try to locate the crater or craters. So Kendall says that it looks like there may be a few small depressions in the upper half. Sarah and Carolyn now said there are 2 craters. 2. Is it one massive one in the bottom left? So it's very interesting that you say that. So I'm gonna go on to the next slide where we can see the crater. So it's actually only just one. So the left, so I'm guessing why people were thinking this one is because it is of lower depression and it kind of looks circular, but that's just the pattern that are created by sort of like the terrain that's in this area. So you can see over here too, there's that lower depression. And usually when you have a crater, the outside, so the rim of the crater sort of is a little bit more elevated. So it's easier to depict it if it's very visibly lower than the surrounding area, which is why this one is not necessarily the crater here. Your purples are actually of even more lower elevation. That's okay, Justin. I didn't get any of this right when I first looked at it. And I just have one last example of this, which I think might be cool. So here we have another radar data. So I'm gonna give you maybe like 2 seconds to try to look and find the crater in this one. Any guesses as to how many craters you see? 1 bottom right. Marshall says 1 in the bottom right. Kendall, Ryan say 2. Okay, so the common guess is 2. 1 top left, 1 bottom right. These are all great guesses. So in the previous one, we looked at how the topography data helps you sort of pick out the lower elevation feature, which could be explained as a crater. What else is helpful with layering different data is it helps you rule out some things. So now that you have the addition of topography data, where your reds are of higher elevation and blues and purples are of lower elevation, it's a bit easier to see that this high elevation feature might actually be more representative of a volcano, whereas this one on the bottom right is the crater. So thank you for participating with me in this little crater identification. But I wanted to give everyone sort of an idea of what it's like to work with remote sensing data and try to draw interpretations from this and how difficult it might be, even though at the same time it's so very useful and it gives us so much more information about a particular planetary body and the surface. So another thing that's very important when we're looking at remote sensing data is the resolution. So for example, when we're looking at these craters, we're looking at very large features, but if we were trying to study sort of, maybe smaller rocks and sand grains, we would need to have finer resolution. So here we have just an image of a feature on Mars where it shows how our orbital imagery resolution has improved over the years with new and new missions going and studying the surface. So it really shows that, so for example, a crater might be easily be identified if we're looking at the middle image, but if we're just had access to the resolution of the very left image, it might be open to so many interpretations, especially without any additional data sets. So those are sort of the main points when it comes to remote sensing. And there's usually an activity to do in person, but because we can't do that, I wanted to share some resources with you. I'm just gonna quickly stop sharing my screen. so that I can open up a different page to share with you all. Okay. So a lot of the sort of like the case studies and images that are shared come from the site Canada Centre for Remote Sensing, which is a really awesome site to learn more about remote sensing, and it has really cool case studies that you can do in the classroom, especially if we're trying to do virtual learning. A common one that many of you might have heard of is Google Earth, where you can sort of look at different patterns and sort of track different regions and look at it over time as well. And this is a great place where you can layer those different data sets that I was talking about. A fun interactive one is something called an Elrock Quick Map. So this is put together by using the images that are collected by the Lunar Reconnaissance Orbiter that's orbiting the moon currently. And it has sort of high resolution and low resolution imagery. So you can play around with this and add different layers. So you can look at different things on, so that you can look at craters, for example, like we just did, and it will point it out for you, which I think is really cool. A fun way to have sort of something hands-on, so something that we just did, where you're trying to identify craters, is this tool called Zooniverse. And they have this fun activity where you can study the different planets. So here, I think it changes over time, but this particular study is for being able to explore the surface and weather of the Mars South Polar region. And it has a tutorial which will walk you through everything. So here they're using images from a high resolution camera on board the Mars Reconnaissance Orbiter that's orbiting Mars. But basically, it's asking the audience to help identify different surface features and help map them, very much like we did with the craters. There's also the Center for Remote Sensing of ice sheets. And I can share this with your moderator so they can send it out to you in an email. But another site is the U.S. Geological Survey, which has a lot of resources for Earth observation and Earth observation science. And a fun one that I like to use and that I have used in the past is something called Jmars. And this is really used for, I think it was introduced to study the surface of Mars, but now it's applicable to different planetary bodies. And it helps you layer data and sort of map in it as well. So I have a quick example here because I can't forget to mention that today the Mars 2020 rover is going to land. So one way scientists study on where to land these rovers is through studying different potential candidates for landing sites. So here you can do a study, and the way a landing site analysis might work is that you look at different minerals that you want to study. So you layer, let's say, you know, silicates and carbonates and olivine. So it doesn't really matter, it's just different minerals that are of interest. And then you can also layer it with, you can map it out. So if I quickly, so here you can see the different units, and then you can use that to map out the different units. So for example, the red here is like a volcanic unit, whereas the blue indicates, you know, past presence of water. And then you can sort of, you know, map out a traverse, if you can see that here. So, you know, help scientists sort of figure out what different units there are and what might we be interested in studying if we send rovers or, you know, potentially humans in the future. So yeah, it was just very exciting that I wanted to mention that the Mars 2020 rover is going to land, and this was one of the studies done to understand the landing site, which I think is really fascinating. So yeah, with that, I will open up the floor for questions. Thank you. I hope this was helpful in learning a little bit more about remote sensing and how you might be able to put this in your classroom.
Yeah, awesome. Thank you so much, Jahnavi. I think we do have a question in the chat.
Oh, perfect. So Sarah asks, for elementary teachers, do you have any simple unplugged activities to introduce remote sensing to students? So there's, it's an in-person activity, which I can share, but essentially it's sort of having like a cardboard box and creating your own sort of like digital terrain model. So you could have it set up for the students beforehand, and what they could do is sort of like, use, so if you have, you could just like really just make your own little like in real life version of, let's say, a mountain, and put sort of like a cardboard box on top, and they could go in and poke with different sticks to see, what's lower, closer to the ground versus something that's more closer to the top, as a way of showing, how we pick at surfaces to sort of map out what might be there. That's a fun unplugged version of introducing remote sensing. Another way is sort of just making use of your senses. So that's a fun way to show remote sensing. So like, if you have an object that you perhaps put in the middle of the classroom and they have to use the 3 different senses that are considered part of remote sensing, and sort of like, taking account of what they see and what it might mean. And then, allowing them to then actually look at it in person and hold it and try to figure out if their interpretation was correct or not.
Do you mind mentioning what those 3 senses were again, Jahnavi?
Yes, so your sight, smell, and sound. Any other questions?
I've got a lot of thank yous for you.
Thank you all for coming.
I had a question for you, Jahnavi. If like one of us were doing like some sort of online placement, would you be able to like make an appearance or maybe do like some sort of activity like how you did with us today, like with the crater interpretations and stuff like that?
Oh, for sure. Yeah, that'd be a lot of fun.
Yeah, that would be cool. Okay, that's good.
And if someone is, really interested in using some of the resources or softwares that I mentioned, and need help sort of like, walking through it, I'd be happy to help if I can with that as well.
Yeah, that'd be awesome. Yeah, I definitely would love to have all those links of the different websites that you showed us at the end there.
Yep, I can put it together. I can put an email together for you, and then you can share it with everyone that was here.
Yes, perfect. That'd be awesome. Thank you.
Yeah. Yeah. So I don't know, I just find it very interesting how I feel like remote sensing, you don't really talk about in school, but a lot of what we study in science is through combination of, remote sensing techniques, and obviously like field studies as well. But yeah, even in the space unit, a lot of the data that we have is exclusively remote sensing data. So I think it's just really cool to sort of introduce that.
Yeah, definitely. And I feel like even like the younger kids are always so interested by like space and stuff like that. And I feel like they think it's really cool. So that's
Right.
awesome.
Yeah.
Great. People might just be heading out because there is another session at 11, but
Yep.
But yeah. If anyone else has any other questions, feel free to ask. We still have about 5 minutes.
Yep.
Oh, we've got a question here. What subjects should students study if they want to go into this type of work after a classroom demonstration?
So see, this is the cool part about remote sensing, is that it's so interdisciplinary. So I think there are some industry things that you can do, especially in Canada, but really anything you want to study, there is access for remote sensing data. So if that's something that you want to do, just stressing that you want to work with satellite data. So like as I mentioned, there's so many applications. So there's space applications, but you can also use it to study agriculture patterns. A fun way to really work closely with this is being involved in a company that works with satellite, because then you're able to work directly with the satellite data. And then obviously, because if you have access to it, you can work on interpreting it for the feature or concept that you're most interested in. And if people want to sort of explore what different things that they might be interested in, or if they would actually like working with it, a lot of remote sensing data is publicly available. So, you know, if a student is really keen, you could share those resources with them, and they can play around with the different data as well. I see another question. Kendall says, I know there are topics, these are topics we often cover in geography curriculum. Do you know of any ways we could better integrate it into the science curriculum? I think we often we don't think of it past topographic mapping, which doesn't get discussed outside of high school geography. I think that's a really good question. And I think one of like a recent, sort of like a relevant way of integrating into the science curriculum is, you know, talking about the aspects of climate change and using that to, you know, sort of visually see how that's affecting it. So for example, looking at images of ice sheets over, you know, the past decade or even the past 20 years and looking at how that's changed. So that's a fun way to get involved with the data and make interpretations of what you see. And then, you know, drawing sort of, you know, the applications of it and what that means in today's world. I think is a fun way to integrate it into the science curriculum. And obviously, like, you know, there's the earth and space science. That's a fun way of doing it. You know, you could talk about different atmospheres. You can talk about studying different surface features. Because I know there's a small space unit, I think sometime in high school, I think grade 9 or grade 10. So that's a good place to have that integrated, I think.
Awesome. Thank you, Jahnavi. And I think your email is on your website, correct?
Yes, it is.
Okay, perfect. Yeah, so that website for everybody is listed in the description for this session. And so you can hit up her website and take a look at it. It looks pretty cool. Look at your blog and stuff. Some pretty cool things on there. So take a look at it. And also her Twitter handle is also in the session description. Is that a way, do you prefer people to reach out to you through Twitter or through your email, or it doesn't matter?
I'm not as active as I would like to be on Twitter. So email would be a way to, if you want a quick response.
Okay, cool. Sounds good. Good to know. Yeah, I'm actually having like I'm going to be in an online classroom in the next month or so. So like maybe I will be in touch with you. See if they're doing a space unit. I don't know. They're kind of young. They're in like grade 5, 6. So we'll see. But that would be cool. So if they are, I will definitely hit you up.
For sure. Yeah, I'd love to be able to help.
Cool. Awesome. Well, thank you so much. I don't want to take up any more of your time. It's already 11 o'clock, but yeah, thank you so much, Jahnavi. That was really cool. I'd never heard of any of this stuff before. So that was awesome. Thank you.
I'm glad. Yeah. Thank you for having me. This was a lot of fun. And I'm
glad
absolutely able to interact in a way.
Yeah, definitely. Yeah. Those always make it a little more fun. So thank you for doing that. That's great.
Of course.
All right. Awesome. So thank you, everybody. And have a good one. Nice to meet you, Jahnavi.
Yeah. Nice to meet you too, Stephanie.
Thanks. Bye.
Bye.
Take care.